Week 8 to 9, Introduction to Support Vector Machines SVM. Welcome to our beginner-friendly lesson on support vector machines, also called SVM. We will use the Pima Indians diabetes dataset to walk through real data mining workflows. By the end, you will know how to use SVM for classification, tune it, interpret results, and spot common issues. Let us get started. Running the cell now. We want to focus on learning and not on technical warning messages. This code turns off all warning messages so we can focus. We import the warnings module and tell it to ignore warnings. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. In this step, we set a random seed for reproducibility and suppress warnings to keep our environment clean. While no output is produced here, these preparations ensure that our SVM results will be consistent and easier to interpret in the following data mining workflow. This lays the foundation for reliable model training and evaluation with the Pima Indians diabetes dataset. What are support vector machines SVM? Support vector machines are supervised learning methods used mostly for classification tasks. They work by finding the best boundary that separates different categories in your data. SVM is powerful for handling data that is not easily separated, thanks to the ability to use kernels. Real-world uses include medical diagnosis, face recognition, and text sorting, just like classifying diabetes status here. Running the cell now. Let us bring in our diabetes data so we can get started. We are setting up our Pima Indians diabetes dataset to use for SVM. We import pandas for handling data. We load the dataset from a public website. We add column names for each feature to make it easy to read. We use pandas to load the data into memory. We print the size of the dataset so we know there are enough rows. We show the first few rows to get a peek at the values. Running the cell now. This output shows the Pima Indians diabetes dataset with 768 rows and 9 columns, including features like glucose and BMI, and the target column for outcome indicating diabetes presence. Noticing the data size and structure is key before applying an SVM, as it helps understand the features involved in classification and the binary outcome we want to predict. Practice: try printing df columns to list out all the feature names. Before we can use SVM, let us check our data for missing or odd entries. It is a good habit to look for missing data or strange values. We count missing values in each column. We also count zeros, since sometimes in health data, zeros can mean missing. The printout helps us decide what to clean. Running the cell now. This output shows there are no missing values in the dataset, which is great for training our SVM model. However, several columns contain a significant number of zeros, especially insulin and skin thickness, indicating potential placeholder values or measurement issues that we may need to handle before classification. Noticing these zero counts helps us ensure data quality and improve the SVM's boundary detection between classes. We will fix zeros in the columns where a zero does not make sense. Many health features should not be zero, so we need to clean them. We list the columns where zeros mean missing values. For those columns, we swap zeros with the median value. We go through the columns and use the median as a realistic fill-in. We check the top couple rows to confirm our cleaning worked. Running the cell now. This output shows the first 3 rows of key health features after replacing zero values with the median, which helps clean the data by removing potentially invalid zeros. Notice how values like insulin now have a consistent median, 30.5, preventing zeros from skewing the SVM model's ability to find a clear boundary between classes. This pre-processing ensures the classifier works with more realistic and meaningful input values. Practice: what would happen if we used the mean instead of the median in this step? Let us set up our predictive problem as inputs and targets. We separate the features we will use to predict from the label we want to predict. X holds all the patient details except for outcome. Y contains just the outcome, which is whether they have diabetes. We print the shapes to make sure the split is right. Running the cell now. The output shows that the input features matrix X has 768 rows and 8 columns, meaning there are 768 examples with 8 features each, while the target vector Y contains 768 labels corresponding to each example. This confirms the data is properly split for training the SVM, highlighting the clear separation between features and labels needed for classification. Why do we split data into training and testing? SVM, like most models, needs to be evaluated fairly. We use some data to train learn patterns, and separate, unseen data to test, to check real-world accuracy. This keeps us from making a model that is only good at remembering, instead of generalizing. Running the cell now. Let us split our dataset so we can train and test our model properly. We use scikit-learn to split data into training and testing parts. The function gives us both the features and the labels, split up. We use 1/4 of the data for final testing. Our split is random but repeatable, thanks to the random_state setting. Running the cell now. The output shows the shapes of the training and testing datasets after splitting, with 576 samples used for training and 192 for testing, each having 8 features. This confirms that 75% of the data is reserved for model training and 25% for evaluation, ensuring the model is tested on unseen data to fairly assess its real-world performance. SVM models work best when features are on a similar scale, so let us standardize them. We use standard scalar to make all input columns have similar scale. Scaling means subtracting the mean and dividing by the standard deviation. We fit the scalar on the training data only to avoid data leakage. We transform the training data into a scaled version. We use the same scalar to transform our test data. Running the cell now. This code standardizes the feature values in both the training and testing sets so they have a mean of 0 and a standard deviation of 1. Notice that we fit the scalar only on the training data to avoid information leaking from the test set. This step prepares the data for the SVM model and ensures a fair evaluation by applying consistent scaling to unseen test data. Practice. Try printing x_train_scale.mean, axis equals 0. And x_train_scale.std, axis equals 0. Fitting a simple SVM classifier. Let us train our first SVM model. We will use scikit-learn's SVC, which stands for Support Vector Classifier. The SVM will try the RBF kernel by default, which handles more complex splits. Running the cell now. Let us fit the support vector machine model on our training data. We import SVC, which is the SVM classifier in scikit-learn. The random_state makes our results repeatable. We create the model, ready to learn. We feed in the scaled training data and the labels, so the algorithm can learn the pattern. Running the cell now. This output confirms that the SVM classifier has been successfully instantiated with the specified random state for reproducibility. It indicates the model is now ready and trained on the scaled training data, setting the stage for making predictions or evaluating performance in the next steps. Notice how the simplicity of this line belies the complexity of the underlying optimization happening during training. Now we will see how well our first SVM model does on held-out test data. It is time to see if our model can correctly predict diabetes. We use our trained SVM model to predict on unseen test data. We get back a sequence of predictions for each patient. Accuracy tells us the fraction that our SVM got right. We print the accuracy as a percentage. Running the cell now. The output shows that our simple SVM classifier achieved an accuracy of 74.48% on the test data, indicating it correctly predicted the class labels about 3/4 of the time. This demonstrates the model's ability to generalize beyond the training data after fitting, which is the key goal of this section. Practice. What do you expect the accuracy to be if you always guessed the no diabetes for everyone? Accuracy does not tell the whole story. Let us look at the confusion matrix for more detail. We want to know not just how often we are right, but what types of mistakes we make. A confusion matrix shows the counts of correct and incorrect guesses, broken down by actual outcome. We import the function, then create the matrix by comparing true and predicted labels. We print it to see where our model does well and where it struggles. Running the cell now. The confusion matrix shows how well our SVM model performed on the test data: 102 true negatives, 41 true positives, with 21 false positives and 28 false negatives. Notice that the model is correctly classifying more negatives than positives, which highlights areas where we might improve the model's balance between precision and recall. This insight helps us understand the model's strengths and errors beyond overall accuracy. SVM kernels, exploring linear versus RBF. Kernels let SVM find boundaries that are not just straight lines. A linear kernel is used when a simple straight line can separate the data. An RBF kernel helps when the split is curvy or more complex. Let us compare both and see what changes. Running the cell now. Let us see what happens if we use a linear kernel instead. We set up the SVM with a linear kernel to see if a line is enough. We train the model just like before, but only allowing straight line splits. We run the predictions on our test data. We compare with the correct labels to get the test accuracy. The printout tells us how well this simpler model does. Running the cell now. The output shows that the linear kernel SVM achieved about 73% accuracy on the test set. This indicates the linear boundary captures some separation between classes but may struggle with complex patterns. It sets a baseline to compare against the more flexible RBF kernel, which can model curved boundaries for potentially higher accuracy. Try changing the linear to a poly. Does accuracy go up or down? The penalty parameter C controls how much the SVM tries to fit every example perfectly. We test a high value of C, which tells the SVM to fit training data closely. We train a new model and see its accuracy. We predict on the test set and record the accuracy. Next, we try a low C, making the SVM allow more mistakes for a simpler boundary. We train that SVM and see how it does. Again, we predict accuracy with the new setting. We print both scores to compare. A high C usually fits more but can overfit, while low C keeps it simple. The printouts show the difference. Running the cell now. The output shows that a lower penalty parameter C, 0.1, results in higher accuracy, 74.48%, compared to a higher C, 5.0, with 67.19%. This highlights how tuning C affects the SVM's flexibility in fitting the data. Lower C allows a smoother, less strict boundary that generalizes better, especially important when using kernels like RBF to capture complex shapes. Grid search helps us test several SVM settings at once and find the best result. We use a tool called grid search to try different SVM settings automatically. We import grid search CV for this job. We make a grid of C values and kernel types to try. The code runs each combo using cross-validation, a way to test on different splits. The model is trained several times to see which setting does best. We print the winning setup. We also print the best average score found during search. Running the cell now. The output shows that the best hyperparameters found were a linear kernel with C equals 0.1, achieving a cross-validation score of about 0.77. This indicates that in this dataset, a simple linear boundary separates the classes fairly well without the need for the more flexible RBF kernel. The grid search successfully identified that a linear decision boundary is sufficient here, reinforcing the idea that kernel choice depends on the data's underlying structure. Try adding polyf to the kernel list above and rerun the search. A ROC curve shows how well our classifier distinguishes between classes beyond just accuracy. Now, we will use the ROC curve to look at our model's performance at many thresholds. We import roc_curve and awk to help plot and score. We bring in matplotlib to make our graph display. The SVM can give each test point a raw score, not just a label. We use these to compute how often positives are caught for each possible threshold. The area under this curve, called AUC, tells us how strong our classifier is overall. We plot the ROC curve with the AUC in the legend for reference. A diagonal line would mean our model is guessing our curve should be above this. We label the axis for clarity. Our title says exactly what we are looking at. The legend tells us our actual AUC value. Finally, we draw our plot so we can see the results on the screen. Running the cell now. This ROC curve illustrates the SVM model's ability to distinguish between classes, with the curve shape showing the trade-off between true positive and false positive rates. The AUC value near the curve measures overall performance, where a higher AUC indicates better separation using the chosen kernel, highlighting how kernel choice impacts classification boundaries in this lesson. Practice: what does it mean if AUC is close to 0.5? Real-world SVM example, predicting diabetes status. Now that you have seen the basics, let us use what we learned in a mini-project. Suppose a clinic wants to screen new patients quickly for diabetes risk. We will use SVM for this classification problem. Running the cell now. Imagine a nurse enters a patient's info to check for diabetes risk using our trained SVM. Simulate screening a new patient by preparing their data. Create a list of the patient's input health metrics. Import the NumPy library for numerical operations. Convert the patient's input list into a NumPy array with the correct shape for the model. Replace any zero values in certain columns with the median values from the original dataset to handle missing data. Scale the patient's data using the same scaler that was used during training. Use the trained SVM model to predict the diabetes risk based on the scaled data. Print whether the patient is predicted to be positive or negative for diabetes. Running the cell now. The output, the diabetes risk positive, shows the SVM model's prediction for the simulated new patient input. Notice how the code first replaces any zero values in key health indicators with median values before scaling, ensuring realistic data for accurate prediction. This step illustrates how the model can be applied in a clinic setting to quickly assess diabetes risk from patient measurements. Try editing values in user_input above and see if the risk result changes. SVM best practices and troubleshooting. Always scale your features before training SVMs, especially if your data includes physical measurements. Try out kernel and penalty options. Defaults may not be best for your data. If your SVM is slow with big datasets, try a linear SVM or other algorithms. Watch your proportions of classes. SVMs can be sensitive if one class is much larger. Look at the confusion matrix and ROC curve, not just accuracy. Running the cell now. Tips for learning SVMs. Try different kernel types. Do not be afraid to try poly or sigmoid for variety. If your accuracy is low, double-check your cleaning steps and class proportions. Grid search is useful for tuning, but you must use test sets for your final answer. Ask for help if you get stuck. Everyone finds SVM tuning tricky at the start. Running the cell now. Let us turn this notebook into a mini-clinic by predicting for user input. Explain to the user what to do, enter 8 numbers separated by commas for a new patient. Read the user's input as a string from the console. Start a try block to handle any errors that might occur during input processing. Convert each comma-separated string value into a float, removing any extra spaces. Create a numpy array from the list of floats and reshape it into a 1-row by 8-column array. Replace 0 values in columns 1 to 5 with the median values from the corresponding data frame columns. Apply the same scaling transformation to the array as was used in training. Use the trained SVM model to predict the diabetes status from the scaled input. Print whether the patient is predicted to be diabetes positive or negative based on the prediction result. If an error occurred in the try block, print an error message asking the user to try again. Running the cell now. This output shows the result of the live prediction using an SVM model on user-provided input data. Notice how the code handles missing values by replacing zeros with median values before scaling, ensuring the input matches the training data distribution. This step is crucial for improving accuracy when experimenting with different kernels like polys or sigmoid, as the lesson suggests. Challenge: experiment with different values to get both positive and negative predictions. Remember to like and subscribe if you are learning. Challenge: how would SVM handle different problems? Suppose you received images, text, or even sensor data instead. What steps would you take to adapt SVM for those? Here is a hint. Feature engineering and kernel settings are important. Try answering in your own words below. Running the cell now. SVM recap: what have you learned? You can load, clean, and split real health datasets. SVMs work by finding boundaries to separate classes. Feature scaling and kernel types matter for success. Go beyond accuracy, look at confusion and ROC results too. Now you can build and tune your own SVM model for other questions. Running the cell now. Thanks for learning SVM with us. Did this notebook help you? Hit like and subscribe for more hands-on machine learning lessons. Feel free to post your SVM challenge answers and questions in the comments. We respond to all learners. See you in the next one. Running the cell now.